Welcome back. We are in the process of proving this theorem which says that if you have a subfield of complex numbers and a polynomial over that field of degree 1, 2, 3 or 4, that polynomial is solvable. We in the last class took care of the cases 1, 2, 3 degrees. Now let us take care of the degree 4. So, of course, we assume that f is irreducible. That is because if it is not irreducible, it is a product of two polynomials of smaller degree, and those we have already considered, right. So, any polynomial of degree 3 or less is already solvable. So, if f is GH, this is solvable means f will be solvable, because any root of f is a root of G or root of H. Okay. So, the only new case is when f is irreducible. So, we are going to assume this. So, hence Galois group of f, which I denote G, of course, K is the splitting field of small f over capital F. So, the Galois group of f is the Galois group of the extension K over f, is a transitive subgroup of S4. Okay, because here there are 4 indices, and because f is irreducible, it is a transitive subgroup of S4. And now, if you think about this, that really what I am saying is, let alpha 1, alpha 2, alpha 3, alpha 4 be the roots of f in K. So, we of course recall here that they are distinct, alpha i's are distinct, because f is irreducible and you are in a characteristic 0 field. So, there are in fact 4 distinct roots, and the G acts on this set transitively because f is irreducible. So, that means given any pair of roots of f, there is an automorphism which sends one to the other. That means we know by the orbit stabilizer formula, I think it is called, or counting formula from group theory. It is, for example, orbit of alpha 1, the cardinality of the orbit of alpha 1 times the order of the stabilizer of alpha 1. Okay. So, there is a map from G to orbit of alpha 1 which sends sigma to sigma of alpha 1, and the kernel is, and this has only things that map to alpha 1 are in the stabilizer. So, using that you can prove this formula. Okay. But this is 4 because G acts on this transitively. Orbit of alpha 1 is the entire set alpha 1, alpha 2, alpha 3, alpha 4. So, this is equal to 4. So, we conclude that 4 divides. So, this is a major constraint on the possible transitive subgroups of S4. Okay, because we are only allowed to have groups of order divisible by 4. That rules out, for example, a group of order 6. It cannot be a transitive subgroup, and in fact, this is a fact. So, this alone is not this observation is not enough to conclude the following statement, but I do not want to prove this group theoretic statement because it will take me far from the main purpose of the course. So, I will simply state this as a fact. Transitive subgroups of S4 are the following. Okay, so I only made this very easy observation to at least rule out things whose orders are not divisible by 4, but you need to do more work to conclude this. So, first is of course S4, second is A4. So, S4 and A4, here order is 12, order is 24 here, order is 12 here. These are both going to be transitive obviously, because you can find given any pair of indices, there is an even permutation which sends one to the other. Okay. The third one is a collection of groups which are all isomorphic to a dihedral group of order 8. Okay. So, there are 3 of them. There are 3 such subgroups. S4 all conjugate to each other. Okay. For example, 1 is given by the sub, so they are all going to be generated by, remember, a dihedral group has 2 generators, D4 has 2 generators, one of order 4, another of order 2, and there is a particular relation between them. So that is satisfied if you take a degree order 4 element, that means a 4 cycle and a 2 cycle, and you can there are 2 more like this. So I don't for now want to write those. This is 1 and there are 2 more. Each of them is in fact a dihedral group of order 8, and this is a cyclic group of order 4. Again there are 3 of these. So there are 3 subgroups of S4 isomorphic to the cyclic group of order 4, and they are all conjugate to each other. For example, you take one of them to be the group generated. So sorry, this is not the set. I should not write like this. This is generated by these 2 elements. So you take those, and here of course you take any 4 cycle and you take the group generated by that. For example, this. So these are subgroups generated by the 4 cycles. So here that is 1. I mean there are 3, but they are all isomorphic to C4. And finally you have D2, which is Klein 4 group. So formally it is a dihedral group of order 4, and this there is only one of this, and this is you take disjoint transpositions. So for example, you take 1 2 3 4, 1 3 2 4, 1 4 2 3. Okay, so each has order 2. So this is order 2, this is order 2, this is order 2. Okay, so this is a group of order 4, but it is not cyclic group, it is the Klein 4 group. So as this observation tells me that the only possible orders of a transitive subgroup of order of S4 are those whose order is divisible by 4. So 24 is one possibility, 12 is another possibility, 8 is one possibility, and order 4 is the final possibility. And you have cyclic group of order 4 or Klein 4 group. So as I said, I am not going to prove this, I am going to assume this, and further I want to separate out these in terms of which of them are in S4, which of them are in A4 and which of them are not in A4. So in A4, of course, there will be A4. 1 3 T 2 4 is odd. Okay, this can be written as I mean this is a 4 cycle. I mean of course this is also odd. Okay, so not in A4 will be D4, S4 of course, D4, and this also is not in A4. Okay, and the last one is in A4 because this is a product of 2 transpositions. So this is even, all these are even. Okay, so there are 5 possible non-isomorphic groups, possibilities for capital G. 3 of them are in not, they are going to contain odd permutations, so they are not in A4, and 2 of them consist only of even permutations, so they are in A4. So now the question is, in all of these cases we want to show that you have solvability by radicals. Okay, so the first observation, which I will immediately write, this follows from the proposition that I proved last time. Let D be the discriminant of F. Okay, then D is a square in F if and only if G is A4 or D2. Correct? So those are the only 2 cases in which D is a square in F. So that in all other cases D is not a square, because that means in all other cases. So, okay, from the above list. And last class, and the theorem from last class. Okay, this is trivial. Now to further analyze, so earlier in the cubic case, discriminant determined the Galois group. It's a square in F means it's A3, it's not a square means it's in S3. So there is no further analysis that is required in degree 3, but to determine which case occurs, we need further analysis. Okay, so we need further analysis, and this is what we do now. Okay, so I am going to define a very important cubic polynomial attached to a quartic polynomial. So degree 4 polynomial leads to something called resolvent cubic. Okay, so let alpha 1, alpha 2, I mean this I noted, but I am going to recall, be roots of F. So I am going to define 3 new elements in K, beta 1 to B. So I will take essentially any 2 of them, multiply them, and then take the other 2 and multiply them, and finally add. So alpha 1, alpha 3 plus alpha 2, alpha 4, finally alpha 1, alpha 4 plus alpha 2, alpha 3. So if you recall the D2, sort of this has close connection to that. I take product of 2 transpositions. So all these are in K. Okay. Now the resolvent cubic of F is defined to be G of X is x minus beta 1, x minus beta 2, x minus beta 3. Okay, so I will do an example where this becomes clear. Okay, so now I claim, I mean this is of course a priori in Kx, and beta i's are in K, so that means this is in Kx, but we claim that Gx is in fact in the base field. Beta i's may not be there, but Gx will be in the base field, the coefficients of G will be in the base field. So the point is, so let us say G, so we will show sigma G is G for all sigma in G. Okay, then G is in KGX, right, because sigma G is in G implies sigma fixes all coefficients of F of G. That means all the coefficients of G are in K power G, but K power G is F because K over F is Galois. So all we need to do is this. But what is sigma G? Sigma G is x minus sigma beta 1, x minus sigma beta 2, x minus sigma beta 3. Now we are done if we show that sigma permutes. So we are done. So this is G if we show sigma permutes the set beta 1, beta 2, beta 3. That means this may be x minus beta 2, this may be x minus beta 3, then this will be x minus beta 1. Okay. So if sigma permutes them, then these 3 factors are just rearranging the original factors. So this will happen to be again G. But why does sigma permute beta 1, beta 2, beta 3? And that is because if you go back to this, so this is an exercise, so this is just a if you go back to the definition of beta 1, this is sigma alpha 1, sigma alpha 2 plus sigma alpha 3 times sigma alpha 4. Okay. But sigma alpha 1 Yeah, so remember sigma permutes alpha 1 through alpha 4. So if you take any permutation of 4 elements and you take sigma of beta 1, this will be some alpha I and this will be some alpha j. These then will be the other 2 elements. Okay, so it will be beta 1 or beta 2 or beta 3. Okay, so this I will leave you to do, because this is much better if you just do this on your own, because instead of explaining this, all I will say now is you take sigma alpha 1, if it's alpha 2 and sigma alpha 2 is alpha 3, then this will become alpha 1 plus alpha 1 times alpha 2 times alpha 3. But then because sigma permutes them, these must be alpha 1 and the remaining things alpha 1 and alpha 4. Okay, so that means that will become beta 3, I think. Okay, so then sigma beta 2 will be something else. So this is just a computation. Okay, so just a computation. This point is important later on in the proof also, but I don't want to do this because this is just this is easy, it's just a computation. So that means G is a polynomial in the base field. Okay, so let me stop that proof there and move on. So that's the first observation. And the second observation, which again I will indicate the proof quickly, is that discriminant of f is equal to discriminant of G. The point is you have constructed a cubic polynomial which has the same discriminant, and they are all distinct. Okay, so the proof, I will not give the full proof, but only observe, for example, the following. So if you take beta 1 minus beta 2, if you go back and see the definition, beta 1 is alpha 1 plus alpha 1 times alpha 2 plus alpha 3 times alpha 4, beta 2 is alpha 1 alpha 3, so the next term will be alpha 2 alpha 4, and if you simplify this, you will get alpha 1 times alpha 1 2 minus alpha 3, and you do alpha 3, so actually alpha 1, yeah, alpha 2 minus alpha 3, then alpha 4 times minus alpha 4, so this is alpha 2 alpha 3. Okay, so this is alpha 1 minus alpha 4 alpha 2 minus alpha 3, correct. So that means this is non-zero, this is non-zero, so this is non-zero, right, because alpha i's are distinct, so beta i's must be distinct. Moreover, discriminant of f is the squares of these things. So beta 1 minus beta 2 takes care of 2 things. Similarly, beta 2 minus beta 3 takes care of 2 more things. So beta 1 minus beta 2 times beta 1 minus beta 3 times beta 2 minus beta 3 will be the product of all the pairs like this. Okay, so this is discriminant of G and this is discriminant of f. Okay, so discriminant is the same for these two polynomials, one quartic meaning degree 4, the other cubic meaning degree 3, and the roots of the resolvent cubic are also distinct. So now we are ready to prove the main theorem about quartic polynomials over characteristic 0 fields or subfields of C. Irreducible of degree 4. Let us say D is the discriminant of f and G is the resolvent cubic of f. Okay, and then let us take K to be the splitting field of f over capital F. And finally, I am just recording all the notations, so which is also called the Galois group of the polynomial f. Then we have the following possibilities. I will draw a diagram, a table really. There are 4 situations. So G is reducible over capital F. G is irreducible over capital F. Remember, G is a polynomial in capital F, right? So, G is in capital Fx. The other on the here I will write D is a square in F, D is not a square in F. Okay, so in these cases we have the following cases. So, in this case G must be the Klein 4 group. In this case G must be A4. So, remember, when D is a square, I already noted we have A4 and D2, and those possibilities are going to be determined by the situation of G, whether G is reducible or irreducible. When D is not a square, we have the other possibilities. So, you have D equal to D4 or G equal to C4, and in this case G is S4. Okay. In this case, this is completely determined. In this case, you have potentially two possibilities, but the degree of the extension will tell you which one will occur, because in here degree is 8, in this case degree is 4. So, if you know the degree and you know the behavior of capital D discriminant and the resolvent cubic, you know the Galois group. Okay. So, these are the 4 possibilities. So, now let me start the proof. So, I do not know if I can finish this, but let me just see how much I can do. So, let me give a name to the set of beta i's. Okay. So, this is 3 elements in capital B, 3 distinct elements, right, that I already observed. So, B has 3 elements. So, now S4 permutes alpha 1, alpha 2, alpha 3, alpha 4. S3 permutes so this gives me a map from S4 to S3, right. So, you take any element of S4 and you apply it to, I mean yeah. So, I do not want to if I will just write like that, but because beta 1 is alpha 1 alpha 2 plus alpha 3 alpha 4, and we already noted that sigma permutes beta I. So, this is that map. So, sigma is a function of from this set to this set, and you can think of sigma as a function from this set to this set. And of course, S3 is sitting, G is sitting inside S4. This is the situation we have. G is in fact a transitive subgroup of S4. So, let us call this map phi. What is the kernel of phi? So, kernel of phi is all the things that fix beta I, that means it consists of elements of S4 which have this property, right. But if you look at this, of course, the identity will be there, it will also contain this, because this fixes beta 1, this also fixes beta 2, and this fixes, because alpha 1 goes to alpha 3, right. So, what is the this D2? So, 1 3 2 4. So, this fixes beta 2 because alpha 1 alpha 3 goes to alpha 1 alpha 3, alpha 2 alpha 4 goes to alpha 2 alpha 4. Similarly, 1 4 2 3 fixes this, because 1 4, that means alpha 1 alpha 4 goes to alpha 1 alpha 4. So, this is 1 3 2 4 1 4 2 3. So, this of course, in my earlier list, this is D2. Okay. So, kernel is precisely D2. Now, we are going to consider okay. So, phi is from S4 to S3 and G is here. So, I am going to consider the restriction of phi to G. So, I am also going to denote that by phi, by abuse of notation. I will use the same phi, and you show that I will analyze this. Okay, so first I want to assume G splits in F. I will analyze this case. That means this is equivalent to splitting. For me always means it's a product of linear polynomials. G is a product of linear polynomials, right? It is x minus beta 1 times x minus beta 2 times x minus beta 3. So that means beta 1, beta 2, beta 3 are in F. But this means sigma of beta I is equal to beta I for all sigma in G, right? Because sigma fixes any element means those elements, if every element of G fixes something that's in the fixed field which is F. So sigma beta I is equal to beta I for all sigma in G. But that means G is kernel phi, right? Because what is kernel phi? These are elements in S4 such that sigma acts trivially. I mean, this is what in words it means. Those things that map beta is to beta is themselves, each beta I to each that beta I is in the kernel. But remember, on the other hand, G from our list, the list of possible G's, it is contained in D2. Now we concluded, but it can't be S4, it can't be A4, it can't be D4 for obvious degree order reasons. It cannot be C4 also, because C4 cannot be contained in D2. Kernel is D2, that I established already. So that means G is equal to D2. Okay. So if G splits completely, the Galois group must be D2. So if G splits completely, in Fx, the Galois group is D2. So that is what I have proved. Now I will consider the case that G is irreducible. Of course, maybe it's not irreducible and maybe it doesn't split completely, but nevertheless I will consider these two cases first. G is irreducible in Fx, but then G acts transitively. See, that is because G is x minus beta 1, x minus beta 2, x minus beta 3, and this is irreducible in Fx. That means any two roots can be permuted by a Galois group element. So G acts transitively on B. That means G acts transitively on 3 means 3 divides order of G. So this is as before. Right, because you take the orbit of beta 1 times the stabilizer of beta 1 is the cardinality of G. Orbit of beta 1 is 3, so 3 divides G. This implies there is only one possibility, right? Two possibilities rather. G is A4 or S4, because I mean I'll maybe just instead of going back I'll write possibilities for G. So S4 degree 24, A4 degree 12, D4 degree 8, C4 degree 3, D2 sorry D4 degree C4 degree 4, D2 also degree 4. So 3 divides the cardinality of the group means it has to be the first two. So G is S4 or A4, that's good. On the other hand, and of course this happens if and only if D is not a square in F. This happens if and only if D is a square in F. Okay. Of course, if D is a square in F, it can also be D2, but in the sub case of G irreducible here. So I am beginning to prove this theorem. If G is irreducible, I have already showed that is either A4 or S4. So this case I have done. Of course, I have to show that this doesn't happen here. That I will show next. Now I consider the case 3 divides the order of, so that means G is A4 or S4. Right. So 3 divides the order of the group, and among the list the only possibilities are these 2, because these numbers are not divisible by 3. So in this case G contains an element of order 3, because 3 is a prime, and Cauchy's theorem says that if a prime number divides order of a finite group, there is an element of that order. That means, say sigma, okay, sigma has order 3. So phi of sigma, phi is the map from G to S3. Phi of sigma has order 1 or 3, because order of an element, order of the image of an element divides order of that element. So phi of, so basically sigma cubed is identity. So phi of sigma cubed is identity. That means phi of sigma has order 1 or order 3. But phi of sigma has order 1 is not possible, because this can't happen, because if phi of sigma has order 1, so this means sigma acts trivially. Yeah, so sigma acts trivially on B. Okay, so let me just leave this as an exercise. I don't at this point quickly recall the statement here, but this is to do with this case. So I will tell you this in the next video, but it cannot be this. So I claim that it has to be this. Okay, let me move on, we will come back to this. So phi of sigma has order 3. But if phi of sigma has order 3 in S3, right? So phi of sigma is in S3, so that means it's a 3 cycle. That means G acts transitively on B, because a 3 cycle already interchanges all. If phi of sigma is 3 cycle, then phi of sigma square is the other 3 cycle, and together they are transitive. So that means image of G contains both 3 cycles in S3. Because phi of G contains phi of sigma as well as phi of sigma square. So that means phi of G is a transitive subgroup of S3. That means G acts transitively on B. This implies G is irreducible. Okay, so this is because if G is not irreducible, you cannot interchange roots of distinct irreducible factors. So if G is equal to H1, H2, and both are degree positive degree, so roots of H1 must map to and vice versa, and roots of H2 also. So you cannot send a root of H1 to another a root of H2. So if it is reducible, G cannot act transitively. So the statement is the Galois group acts transitively on the roots of a polynomial if and only if the polynomial is irreducible. So G is irreducible. So what we have shown is, if G is irreducible, G is equal to S4 or A4. If G is equal to S4 or A4, G is irreducible. So in conclusion, G is S4 or G is A4 if and only if G is irreducible. Okay. So I am sorry, I am going fast about this, and maybe this is just too much material to grasp in a video, but please pause it, watch it multiple times if needed to conclude what I am writing here. So essentially this slide here contains the proof that this equivalence. If G is irreducible, you concluded that capital G is S4 or A4. On the other hand, if capital G is S4 or A4, we have concluded that small g is irreducible. And now I claim that we have finished the proof. We have finished the proof of the theorem because, okay, maybe I will write the proof here, the statement here. So, d square in F, d not a square in F, G reducible, G irreducible. Okay. So, this is A4, this is S4. I hope that is what I wrote. Yeah. So, this bottom row I have established conclusively. If G is A4, then it is irreducible. G S4, then it is irreducible. If it is irreducible, then it is A4 or S4, and where they fit in depends on the discriminant, whether it is a square or not. So, the other case is this. In this case, you have only 3 possibilities. So, these are when G is irreducible, these are when G is reducible. When G is reducible and capital D is a square, it has to be D2, right? Because only possibilities are D2, C4, D4, but the cases of C4 and D4 are not, I mean, in that case capital they contain odd permutations, so D is not a square. So, finally, we have D4 or C4. Okay. So, this is done, and in fact, I want to write, so this finishes the proof, and I want to summarize this in a better way in the following statement. So, in the above setting, same as above, G splits completely in capital F. This implies G is D2. In fact, you do not need to worry about whether capital discriminant is a square or not, because if G splits completely, we have showed that G is small g splits completely, G is D2. So, I wanted to write this here. If G does not split completely, but it is not irreducible, that means it has exactly one root, right? Because if it has 2 roots, it will have the 3rd root. So, if it is reducible, does not split completely, that means it has exactly one root. So, this is a convenient way of doing this. So, this is if and only if. Then in this case, G is either D4 or C4, if and only if again. The third one is G is irreducible if and only if G is S4 or G is A4. Okay. So, by looking only at the behavior of G, you do get lot of information, and to separate out these cases, in the second one, you can't separate out these cases by discriminant, because they both occur when D is not a square. You can only separate it out by looking at the degree or the order of G. In the third case, you can separate it out by looking at the discriminant. So, I hope this is clear. The proof essentially gives you this. Okay. So, now finally, the statement. So, capital F is a subfield of C, small f is a polynomial, degree f is less than or equal to 4, then f is solvable over capital F. Okay, the proof. So, this is our goal, right? In these 2 videos, we are trying to prove this. First, we have already taken care of the cases 1, 2, 3. So, now let F be degree 4 irreducible. So, now what I do is, I do the following chain tower. So, I start with F, let delta be the square root of D. So, I will take f of delta. This is either degree here right? So this degree here is 1 or 2. Why is that? It is 1 or 2 depending on whether delta is in f or not. In other words, d is square or not. If d is a square, it is 1. If d is not a square, it is 2. But now look at f over this. Consider f over f delta. Here discriminant is a square. Right? Discriminant is a square now because we have attached the discriminant. The polynomial is the same, right? The polynomial is still f. Its discriminant is still capital D. The square root of the discriminant is still delta. But now in our base field, discriminant is there. Okay. So now take the splitting field of the resolvent cubic over f delta. So you have L here. Okay. So now this is a degree 3 polynomial over a field f delta. So this is solvable by case 3. Right? Because we have already taken care of degree 3 polynomials. So this being the splitting field of a degree 3 polynomial is solvable. Now consider the same polynomial f over L. Right? Now the point is G resolvent cubic stays the same. Again, f is the same f, resolvent cubic is the same. So G splits completely over L. Right? So now you can consider the splitting field will be the same, capital K. See, because along the way you have to add roots of all the, you have to add delta to get roots, and you have to also add beta 1 through beta 2, beta 3 are all in K. So all of this is happening within underneath K, and this is degree 4. Remember, if G splits completely in F, then G is D2, capital G is D2. So this is D2. So Galois group of K over L is isomorphic to D2. But now D2 is solvable because you can write L over K, L as L prime K. So this is degree 2, this is degree 2. Okay. So now in summary what we have is, so this tower I will write in more detail. We have the following tower. So we have F, F delta and L, L prime K. So this is degree 1 or 2. This is solvable. This is 2, this is 2. And all the roots are in K. So the point is delta is in K, beta 1, beta 2, beta 3 are all in K. So F delta, L, L prime are all in K. So this is a tower. So now this is degree 2, so this is cyclic. Of course, this is solvable. So it can be a tower of cyclic extension. This is cyclic. This is cyclic. Okay. So you have a tower of cyclic extensions containing all the roots. So hence F is solvable over capital F. Okay. So this is a beautiful argument, right? So you have all the roots living in a field which is a radical extension, okay, by our general theorem that we have proved. Remember that theorem allows, so that theorem is crucial here because we are not talking about radical extensions here at all. I am not saying that each of them is obtained by adding a radical. I have taken care of that in my previous theorem, and now I am only saying that each of them is a cyclic extension. Okay. So capital small f is solvable over capital F, and this finishes the theorem. Okay, so I have taken a lot of your time in this class, I am sorry about that, but let me end this class by the following remark. So there are formulas for finding roots of degree 3 and degree 4 just like quadratic polynomials. Okay, so the name that you see here is an Italian mathematician called Cardano. So you find out, if you search in various books or on the internet, you will find that Cardano gave formulas for degree 3, degree 4, but these formulas are not very useful because there is a lot of ambiguity about when you take roots, fifth root, third root, fourth root, it's not clear which roots you have to take. So there is some ambiguity and hence they are not very useful. However, we have conceptually proved that there would be formulas using radicals, okay, by using this. So our proof establishes that roots can be solved using radicals. So rather, polynomials can be solved using radicals without giving explicit formulas. Okay, so we don't necessarily give explicit formulas because that's not clear, right? We are conceptually saying that all the roots are in a tower or in a field, and there is a tower starting with that field, ending with the base field, where each of them is a cyclic extension. So now I don't, so maybe I should really write here. So this is a degree 2, maybe L double prime. So this is 2 and 3, or this is 3. So I don't want to write solvable, but to say that everything is cyclic. So there is a tower of cyclic extensions ending with a field containing all the roots, so it is solvable. So we don't necessarily have formulas, and often we do not use formulas. We don't need to compute the roots explicitly because the formulas themselves are often ambiguous and hence not useful. But conceptually we have established that degree 4 polynomials, degree 3 polynomials, degree 2 and degree 1 polynomials can be solved by radicals, and next we will take care of degree 5. And before that, I am going to give you alternate proofs of these statements in the next class using solvable groups. So let me stop this class here, and in the next class we will continue studying solving polynomials by radicals. Thank you.